So I really dislike this unit because I haven't figured out a good way of figuring out all the way of presenting it because of how interlinked that is. There's the heat equation, there's the gas laws, and then there's the work equations, work and heat, the work equations. And you really need to know all of them. And if you've seen, there's a lot of equations for this unit. Thermodynamics is very, very complicated. Because basically what we're doing is I'm telling you there's a billion atoms. They're all moving in random directions. They're all colliding with walls, bouncing off of each other, and doing something. And I'm going to simplify it all down to a few equations. Think about all the kinetic energy they have and how that translates. So it's a very complicated thing. There's one equation from the gas laws I want to introduce. We're going to go into the gas laws later. But it's a way to relate pressure and volume to number of moles and temperature. This is called the ideal gas law. If we have an ideal gas, then we can take the pressure, multiply it by the volume, and it'll equal the number of moles times the gas constant times the temperature. And this is true for any ideal gas. An ideal gas is a gas that has these assumptions. One, the molecules are small enough in relation to the container to be considered point-like objects. Which is true for most gases. It's true for the air we're breathing right now. So atoms are very, 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 very small. And this room is extremely big. You can, if we were to freeze all of the, or not freeze, but liquefy, if we were to bring the temperature of this room down to the point where the air begins to liquefy, all the atoms in this air would probably fit inside my desk if you were to cool it down. They get spread out tremendously far so that they're not really cramped. So, an example of a non-ideal gas is if you have if you take all the air in this room and you put it in a very small container that's under an extreme amount of pressure. There, all the atoms will be so close to each other, all the gas molecules, that it would almost be liquid. You can almost no longer call it a gas. It may have enough kinetic energy that they're all able to move around, but they're so closely packed together that it's hard to it would be mathematically different because of how close the atoms are forced to be together. But in normal environments like what we're used to, this is a very good assumption. This is true for most gases. 2. The gas particles don't interact with each other. Other than by collision. What this means is, so let's look at nitrogen. Nitrogen is N2, so it's a nitrogen atom bonded to another nitrogen atom. Can you please come to the front office, please? Come to the front office. And this is a neutral atom. It has no charges. More importantly, the charge of the individual atoms that make up this molecule is also neutral. This nitrogen doesn't pull any stronger on the electrons than this nitrogen. This goes more into chemistry. But if we look at water, for example, water is H2O. The oxygen atom pulls more strongly on the electrons, so it gets a negative charge, and the two hydrogens become slightly positive. What this means is if I instead put another water molecule next to it, the negative oxygen and the positive hydrogen will be somewhat attracted to each other. And so there will be an additional slight force just due to the attraction of the molecules. In an ideal gas, we assume that there is no interaction between them other than when they hit. Which is true for most gases that we deal with. Nitrogen, oxygen. Oxygen is O2. Nitrogen is N2. Helium. Helium doesn't react with anything. And if it behaves like this, then it very accurately works by the ideal gas law. So let's do some examples. That's out of the way of the problem we were doing yesterday, or the equations we're doing yesterday. So how much work is required to compress a monatomic? So your monatomic gases is your noble gases. Ideal gas at a pressure of 2.5 times 10 to the 5 Pascal from an initial volume of 0.015 cubic meters to a final volume of 0.010 meters cubed. And the question is, what is the change in the internal energy of the system? If the system releases 350 joules of heat in this process. So we can think of this as a box. So imagine we have a box. And it has some gas inside of it. And we have this piston that is pushing it inward. So we have this piston that is going inward, that is pushing in this direction. So initially the volume is 0.015 cubic meters. And we're wanting to push this piston in to make this, to compress the gas. We're trying to figure out the total energy and also the work involved. So we're trying to push it in. So now has a volume of 0.01 meters cubed. So when we push it in, this piston is going to slide on the side of the box. So it's going to generate some sort of friction. That friction is going to correspond to heat, and that heat is going to leave the system. So what we're putting into the system is only work, and what's leaving the system is heat. And we're trying to figure out how much energy is being stored by the compressed gas. A Pascal, I should mention, we haven't seen this unit before in this class, is a Newton per meter, I believe. Let me make sure. By the way, this is about, I think, 2 point. I'll look it up. So Pascal is equal. So 1 Pascal is equal to 1 Newton per meter square, or a kilogram divided by a meter second square. Newton per meter square is probably the best explanation. Atmosphere, this room. So 1 atmosphere pressure is 101,000. This will give you an idea. 325 Pascal, are 1 times 10 to the, about approximately 1 times 10 to the 5 Pascal. So this is about 2.5 times atmospheric pressure. So we know our equation for change of energy. Change in energy, internal energy, is equal to, what do I do with the, do you have it? What's it say? I was formatting the equation for you. What I'll do with my copy of this. Let me have to look away. I'll just look it up. I got a copy. Heat minus work. Where my cheek? My computer's very laggy. So, and how did I define heat? So if we have a a system that we close, so that would be the box. So we have a system and we have surroundings. Q is heat going into the system, and work is work done by the system. Do we have heat going into the system? So that means Q is going to be equal to negative 350 joules. It's negative because we need to flip the sign of the arrow. And this at this point, so you have a good guess. What'd you say? Isothermal? Well, if heat is leaving the system due to friction, do you think temperature is going to stay the same? Let's just continue. So this system, let's see. I think that this system is most likely going to be isobaric. Same pressure. So basically, as you squeeze this gas, it's going to heat up, and when it heats up, that heat is going to leave the system, lowering the pressure. So remember, if you decrease temperature, pressure goes down. So I was kind of wrong earlier whenever I said that it's going to be due to friction. It's not due to friction that is done. It's just that the heat generated by compression is going to leave the system. But this is an example of, if we look at work is equal to force times distance. And if you remember, pressure is simply force divided by area. And so if we look at the area of this piston, so if I multiply A to both sides, we get pressure times area is equal to force. So work is equal to the pressure times the area of the piston times distance. And if that's the area, so length times width. So pressure length times width. And then this is the distance we moved. So going from here, distance. Are just basically distance times length times width is just volume. And the work is going to be a change. We've already went over this yesterday. It ends up that it's just pressure times delta V, right? So we can calculate work. Work would simply be so our pressure would be 0.015. That's not. Our pressure is 2.5 times 10 to the 5 Pascal. And our change in volume is final. So 0.01 cubic meters minus initial 0.01 cubic meters. So our final work, our total work done by the system into the system, that should be a 15. is negative 1,250 joules. Or Newton times meters. Remember, work can also be Newton times meters. But we'll keep it joules just to make the numbers work out. We get a negative sign. Does this make sense? So work is defined as the work done by the system. However, the problem says that we use work to compress the piston. So, because our definition of work in an example is where when work is positive, it's done by the system. If we want to negate this and do work on the system, we have to make it negative. So this negative value makes sense. So what is the total energy done by the system? Well, we know Q is negative 350 joules, and minus the work, which we calculated, negative 1,250 joules. This is equal to negative 350 joules, negative and minus, make it plus. And we see that the total energy of the system was increased by 900 joules. Make sense? So in this problem, it's kind of hard to have seen that this was isobaric. Most problems I give isn't going to be that unclear or ambiguous. The important thing here is it says releases this much joules. If it releases this much joules, that means heat is leaving the system. And heat leaving the system usually causes a change in temperature. And a change in temperature can regulate pressure. If your pressure is, or if your temperature is leaving at just the right rate, you can get the pressure to stay constant. Another thing that you can think about too is we're looking at a point in time when enough heat energy has lost that the pressure is re-equalized. So let's do another problem. So 4.5 moles of an ideal gas. The beauty of ideal gases and doing this is we don't have to specify mass. We can just specify exactly how many particles of that, how many molecules of the gas there is. So recall that moles is 6.022 times 10 to the 23 particles. It's like a dozen, except for much bigger. So 4.5 moles of an ideal gas is heated at a constant pressure from 30 degrees Celsius to 150 degrees Celsius. Calculate the work performed by the gas. And draw a pressure volume diagram for this process. So, it tells you constant pressure. So it's isobaric. Looking at your fancy table, we have two equations for work. Work is pressure times delta V. And work is also equal to nR delta T. We're given the number of moles. This is your N. And you don't need this information. We're given a change in temperature. Recall that change in temperature can be in Celsius. And the only thing you need to know is R. That's a number you just look up on the table or below the table or find it. So we can calculate the work. The work would thus be so nRT delta T. That would be 4.5 moles. And the R value that we're going to use, R is equal to 8.3145 joules per mole Kelvin. R is thus, we can plug that in, 8.3145 joules per mole Kelvin. That's just a constant, never changes. At 150 degrees Celsius minus 30 degrees Celsius is equal to 120 Kelvin. So change in temperature, again, you can convert changes in temperature to Kelvin here in degrees Celsius. So we can plug 120 Kelvin in. Kelvin cancels out, mole cancels out, leaving us with just joules, which is the measure of work. And we see a total work done is 4,489.83. So let's draw a picture of what's going on. So a PV diagram. We have pressure on the y-axis, and we have volume on the x-axis. So it says an ideal gas is heated at a constant pressure from 30 degrees Celsius to 150 degrees Celsius. If you keep pressure constant, so pressure is constant, and you increase temperature, what happens to volume? Volume increases. So I'm going to mark some initial volume and some initial pressure. And this is going to be my initial pressure and initial volume. As I heat it up, it's going to stay at the same pressure and go to a new volume. So this corresponds to 30 degrees Celsius, and this corresponds to 150 degrees Celsius. There's a 3-hour video showing examples and explaining this. I'm trying to nitpick the very best ones from the video. It also goes into a lot of the explanation. Yeah. do some more examples. The pressure of a gas inside a rigid 2.4 liter cylinder is decreased from 4.8 atmospheres, this is a unit of pressure, to 3.4 atmospheres. How much work was done by the system? If you ever want to be a mechanical engineer that builds new fast supercars, this is mainly going to be your job. If you're doing engine design, is studying how a piston in an engine works and the transfer of energy and so forth. Thermodynamics. Alright, so how much work is done by the system or on the system? I'm asking. How much work is done by the system or on the system? Remember the definition of work. Work is equal to force times distance. What is moving? What piston? This is a completely sealed container, hence the word rigid, which means that the volume is constant. So nothing is moving, so work is zero. You have to interpret what some of these mean. When it says, whenever it says you're compressing the gas, you're doing an action, you can think of it like a piston, where the only way to compress the gas if you're somehow mechanically pushing on the gas. That's the only way. You have to do work on it. If it says that the cylinder is rigid, it's usually saying that you can't push on the gas inside. That's in a sealed container. Which means the only way you can increase the pressure or decrease it is by changing temperature. So basically, this is a zero work problem. So it says the 2.4 liter cylinder is rigid, meaning it doesn't change. So work equals pressure change in volume. The change in volume is zero. Anything times zero is zero. I want to do an adiabatic example because it's on the one, but I also want to do something else. You should at least be able to do a few of the homework problems over this. I want to go over one other thing and then go into the lab very briefly. What's it called? Ideal engine. What's the ideal engine? Carnot. I'm pronouncing it horribly wrong. So the ideal engine, or I should say, the Carnot heat engine is a theoretical engine that operates on the Carnot cycle. It was mathematically proved that you cannot build an engine that is 100% efficient. Let me see, the Carnot, what's the efficiency on a Carnot engine? A Carnot engine is one of the most theoretically efficient engines. And how efficient do you think it is? So basically, it looks something like this. We have a volume and a pressure. It's a cycle, so it's going to repeat. So if you were to increase the pressure, you can only do that by decreasing the volume of the piston. However, as you decrease the volume and increase the pressure, temperature is going to be, so this is T1 and this is T2, temperature is going to then decrease. And then as you increase the volume of the piston, I'm still drawing it wrong. Let me draw this better. So as you increase so as the piston goes down, then it's going to do the temperature differences, some of the temperature. As you actually use work, some of the work is going to be gone out, and then as you up in the piston, and then it's going to look something like this. We see heat losses during this, or losses of energy. I believe it can only be like 60 or 40% efficient. Which means the most ideal by the way, in order for there to be any work, you have to have a temperature gradient. So this is the temperature gradient between 2 points. The bigger it is, it looks like something like this. It's hard to explain this. I have a Stirling engine I want to show you. You know what a Stirling engine is? Alright, let's go to a